Hello and welcome to this sixth video on high-frequency design with a microwave office. I haven't posted one of these for a while. Earlier this year I had some problems with my microwave office license, and as soon as we got those straightened out I had some other things that I had to do that sucked up all my time for a few months. But now I'm back into doing this, and I hope that I'll be posting them a little more often from now on. Today I would like to show you some information about frequency multipliers, FET frequency multipliers, or in general active frequency multipliers, although I'll be focusing mainly on FETs. These are very practical components, and they're actually fairly easy to design and to get them going. I'll start with a little bit about the theory and finish off by showing you a design example. Okay, so let's talk about how we make one of these things work optimally. Here is a circuit, very simplified circuit, of course, of a FET frequency multiplier. We're driving it at the gate with some sort of an excitation and, of course, gate bias. And at the output, we filter the output with a tuned circuit. This, of course, is a parallel tuned circuit and a load. It's tuned to the second harmonic, or to the harmonic you're trying to generate. And we'll see in a little bit that trying to generate anything higher than second or maybe third harmonics doesn't exactly make a whole lot of sense. Now, to optimize this, there's a couple of things we need to do. The first, as I mentioned, is we want to maximize the second harmonic current in the channel of the FET, or the second harmonic drain current. And then we want to select the load resistance in such a way that we get the maximum output power, which means the highest voltage for a given second harmonic drain current. That's the trick that we need to do. Now let's take a look at some of the waveforms in this circuit. First, at the gate, we've biased the gate at some voltage VGG, which is usually well below the threshold or pinch-off voltage, which I'm calling VT. And then we have, of course, a sinusoidal excitation. Whenever that voltage is above that threshold voltage, we're going to get a pulse of current. And the larger the voltage, of course, the greater the pulse of current, up to the point where we reach some kind of a maximum. In a junction FET, that'll, of course, be the point where the gate-to-channel junction turns on. In a bipolar device, it will be the base-to-emitter diode junction, which turns on at about 0.7 volts. And in an insulated gate device, it's a little less clearly defined, but there's going to be some maximum that you can reach anyway. So as long as that voltage is above threshold, you'll get a pulse of current. You apply that pulse to that resonator in series with the FET drain, and you get a voltage. The resonators tune to the harmonic. In this case, I'm showing the second harmonic. And so we get a second harmonic component. Note that there's only a second harmonic component. You can't really see any fundamental or third harmonic in here because the channel, the drain, is shorted to the source by that resonator at all their harmonics. It only will support a single harmonic, which is the desired harmonic. So this is what's happening in any device. We get these pulses, and those generate a second harmonic output. Now, how do we optimize that output? Well, we're going to optimize it by first making these pulses as large as possible, and we can control the duty cycle of those pulses, which turns out to be important, by adjusting the bias, and that will determine what fraction of this waveform is above threshold. So that gives us a duty cycle. Now, I said earlier that we want to maximize the harmonic current in that pulse. If it's a frequency doubler, we want to maximize the second harmonic, tripler, third harmonic, and so on. Well, how do we do that? Here I have plotted the harmonic current component as a function of the duty cycle of that pulse. And I've assumed that the pulse is a rectified sinusoid, which is not exactly right, but it's not far from being correct either. As a matter of fact, if you approximate it even as a square pulse, you're not much different from this. So this is a reasonably good way to look at it. For the second harmonic, we find that we get the maximum second harmonic current component at a duty cycle of, what is this, about 0.33, although it's a fairly broad optimum, and the current is about 0.27, 0.26 times the maximum current that you get in the device. The maximum current, of course, is defined by the IDSS and a FET. Again, in a bipolar, it's not quite so clearly defined, but there's still going to be some sort of a maximum that you have to stay aware of. Now, if you're making a tripler, you start to see the problem here. First of all, the harmonic component is smaller, and the duty cycle is smaller. Now, the way we get that duty cycle is, of course, by adjusting the gate bias, so that in the case of a doubler, where we said the optimum is about 0.32, 0.33, we want to adjust the gate bias, making it negative enough that the gate voltage is above threshold only for about that fraction of the waveform. So you have to make the gate bias pretty negative to do that. For the tripler, it's even worse. You have to make it even more negative. For the fourth harmonic, the quadrupler, you have to make it about duty cycle of about 0.18, 0.17, something like that. And that turns out to require a very negative gate bias indeed, probably so low that you will exceed the limits of the device. So it's hard to make a good fourth harmonic multiplier. It's possible, but more difficult than a doubler at least, to make a third harmonic. And the doubler turns out to be very practical after all. So this is why I said earlier that doublers are real practical. As you go to higher and higher harmonics, they become less and less practical. Now, what if you want to make a fourth harmonic multiplier anyway? Well, you end up having to work to operate it on this part of the curve somewhere around in here. And that means you're going to get less output. The fourth harmonic current in that pulse is going to be smaller, which means the output power is going to be smaller inevitably. And so you're going to end up with a rather inefficient quadrupler. It might make a lot more sense to have two doublers, for example. If you want a tripler, well, that's getting along to the borderline of what's practical, but it still is a reasonable thing to do. Quadrupler gets to be very difficult, though. Now, the final thing to determine is the output loading, and that's actually pretty simple if you think about it for a minute. We saw that we wanted the output voltage here, VL, to swing between some Vmax and Vminimum, with the drain bias voltage here between the two. So what we want is a voltage whose magnitude is that Vmax minus VDD. The current we saw, we can get from those curves you saw a second ago. And so the current times that resistance should be that voltage. This is very similar to what we have in a power amplifier, if you're familiar with that. So we have this current component times the resistance is Vmax minus VDD. And that's really the whole story. Now, the rest of the design is about what you would expect it to be, I imagine. You want to match the gate to the excitation, the fundamental frequency excitation, and that's largely the same as any other amplifier. Certainly it's the same as any power amplifier or large signal amplifier. It's a good idea, but considerably less important, to try to short circuit the gate at the harmonic frequencies. And that's not terribly difficult to do, as we'll see in a minute. The drain, of course, we want to realize this with some kind of a microwave circuit, obviously, some sort of matching circuit, probably using transmission line stubs and such things. But we still want to achieve something that does what this does, namely it shorts the drain to the source at all the unwanted harmonics and lets through the wanted harmonic. I'm going to think primarily of a doubler in these cases because, as I said, that's the most practical thing to make. Now, before we get too far along, I'd like to say a little bit about input matching. And this, of course, applies primarily to frequency multipliers, but it also will apply to Oh, FET resistive mixers, active mixers, and a number of other circuits that we're going to talk about as time goes on. Now, the situation we have with any FET is that the input impedance at the gate looks like a low resistance in series with a capacitance. The capacitance is primarily the gate-to-source capacitance, and the resistance is a number of resistive parasitics. The point is you have some resistance and capacitance. Now at low frequencies, you can see what's going to happen here. This capacitance will have a fairly high reactance because great modern devices have very low gate-to-source capacitance and very small resistive parasitics. And as you go to higher frequencies, this reactance will get lower and the resistance will be comparable. But in any case, you're always matching into an RC circuit. At low frequencies, you're matching into something that appears to be practically an open circuit, which is kind of difficult. And at higher frequencies, you're matching into a capacitive reactance plus a resistive reactance. So that's what your matching circuit should look for. Now, at the higher frequencies, it's possible to get a conjugate match. This resistance is fairly low, but you can still do it. The question is whether it's advisable. At low frequencies, though, you don't have a prayer of trying to get anything like a conjugate match. So how do you deal with this situation? Well, one way to deal with it is to approach it the same way the analog electronics guys do, at least at the lower frequencies. So you can say, okay, we have a capacitance here, we have a source impedance over here, and a little bit more resistance over here. That gives us a real pole. It's 1 over RCGS, right? So we try to keep the resistances small enough so that that pole stays above the frequency at which we're operating. And that you can usually do fairly well. It just depends on what the resistances are and what the frequency is that you're using. Okay, now think about this for a minute. As we make this resistance higher for a given available power, the voltage, the open circuit voltage at this point, which is what's important because this capacitor, as I said, is almost an open circuit. This open circuit voltage will be high as well. So you make this resistance as high as you can, consistent with adequate bandwidth, and that gives you the maximum transfer between this source and the load, and therefore the maximum gain in the multiplier. Well, that's fine for lower frequencies, but I'm a microwave guy. I suspect if you're watching this, you're a microwave person too, and that probably doesn't provide much help for you. So the knee-jerk reaction when you have a circuit for all microwave guys is to conjugate match things. Well, can you really conjugate match this? Does it make any sense to try? What you need to do, first of all, is have this impedance be inductive, so it resonates this capacitance, and the real part should be equal to this resistor, so you get a conjugate match. Apply some numbers to that if you wish, and you will find that anywhere short of the millimeter wave range with any reasonable device, you're going to find yourself with a huge Q, and it's probably not going to be realizable in any practical way anyway. So what do you do to get the bandwidth, to get the best match that you can, which means the greatest power transfer into CGS? So here's what I suggest. First of all, you select the source impedance to resonate CGS. That's what you have to do. You have a series resonance that maximizes the voltage across CGS. Now, as far as the real part of the source impedance, you're not going to be able to match this resistance. It's just too low. And you don't want to anyway because the Q will be too high. So the best thing to do is to select this resistance based on the bandwidth of your circuit. So you keep the Q low enough so that you get adequate bandwidth. And that's the simplest thing to do. Now, if that doesn't work, you have to look into more complicated matching circuits, and then it gets a little sticky. There are synthesis programs that will help you synthesize a matching circuit. I don't use them very much. I almost never have had to. But there are things like that that you can do if you're in a situation which requires greater bandwidth than you can get with these simple methods. So anyway, that's the idea. And let's now take a look at a design and see how it goes together. Here's one way to realize doubler. I used to do this quite a bit back in the early days, although today it's probably not as well suited to the kinds of circuits that we're making because it tends to be fairly large. But anyway, at the input, we have a fairly conventional matching circuit. We have a series, high impedance line and shunt, low impedance stub, so it kind of gives you a series L shunt C matching. The bias is inserted through a quarter wavelengths high impedance line. Now I also have a capacitor here to short circuit this point at higher frequencies, and that means this is a half wavelength long at the second harmonic, so it easily short circuits the the gate at the second harmonic, which is what I said earlier we want to do. Now let's take a look at the output. In the output, the main thing you'll notice here is this series of high impedance, low impedance, high impedance, low impedance lines. They're a quarter wavelength long at the fundamental frequency. So whatever loading impedance we have here is transformed to a high impedance, to a lower impedance, higher, lower, and you get a very low impedance here. So that's a good short circuit at the fundamental frequency. Furthermore, if you make several stages of this, as I have shown here, you will get a nice broad band short circuit. It really works out very nicely. The only downside, of course, is that it's fairly large. Now at the second harmonic, these are going to be a half wavelength long. So they're, again, theoretically invisible at the second harmonic. They look like just series lines. And then finally over here, we have some matching largely to compensate for the reactive parasitics in the FET. We have DC block for obvious reasons, and we have injection of the DC voltage. Now let's crunch a couple of numbers here. Typically we will want the swing to be about 2 volts, positive and negative, around the DC bias point. So we want about 2 volts, let's say. That gives you from close to 0 to about 4 volts if this is biased at about 2 volts. Now, for the current, remember we said the optimum current was about 0.28 times the maximum current. That is, the second harmonic current is about 0.28 times the maximum current. So let's take a look here. Say the maximum current is 200 milliamps. 200 milliamps times 0.28 is 56 milliamps, and 2 volts over 56 milliamps comes to about 36 ohms. That's a very convenient loading value here. It's getting quite close to 50 ohms. You could probably twiddle things a little bit so that the load would be very, very close to 50 ohms. You wouldn't have to worry about much except compensating for some of the reactive parasitics. So the numbers for a frequency doubler all seem to fall into place rather nicely. Now, just for fun, I thought I would show you this. I'm sorry the picture isn't much better. This is the only copy of it I could find. It's pretty small. Dates from the early days of digital photography, so it's necessarily small. But anyway, this is the first FET frequency doubler I ever made. And you can see it's made entirely according to the circuit that I just showed you. There's input matching. Here is the bias and the capacitor, a stub, quarter wave stub at the fundamental frequency, and this is a quarter wave at the fundamental frequency, so it also short circuits a second harmonic. This output circuit is the same as the one that I showed you, and it really didn't require much extra tuning. You can see a little bit of copper foil here and there. And of course, this is on a composite substrate. And that's the whole thing. Now, the story behind it is that I did my PhD work on active FET mixers. And at one point, I realized that the LO analysis for the FET mixer could be used For a frequency multiplier, you just take the output at the second harmonic. And that's really the only difference. It's very easy to do. So I ran some numbers and I found that it predicted a gain of about unity, a dB or so, between 5 and 10 gigahertz. That is 5 gigahertz in and 10 out. And it predicted about 10 dBm output. And that would be perfect for a frequency multiplier for an LO chain in a mixer. So I went down to the lab and quickly put together a circuit using just ordinary tape. It might have even been, cellophane tape as resist, and came up with this, put it together, and it worked. So I was quite happy with it. It did essentially what I predicted it would do. And I started thinking about publishing it until I picked up my copy of the MTT transactions, and there was a very nice paper on FET mixers by Christian Rauscher of the Naval Research Labs. And after reading that, I thought, well, this guy's gone so much farther with it than I have. I'm not really going to try to publish it. It didn't make much sense if indeed I could get it accepted in the first place. But anyway, that's a story. That's an example of one. And just the fact that I could do it so quickly and easily shows how practical these really are. Now let's turn to Microwave Office and take a look at an example. This is going to be an example of a FET frequency multiplier, a doubler, 5 gigahertz in, 10 gigahertz out, and we'll try to get about what you usually get out of such a circuit, which is approximately unity conversion gain and something like 10 dBm or a little bit more out of it. Now, when I begin with a new design, with a new set of models, whether they come from a foundry or from a device manufacturer, I like doing a sanity check on the device, because a lot of the models you get these days are really not very good. And so it really helps to just check them, make sure what they do is something that makes sense before you put a lot of time into the design. So let's take a look at the FET model here. The model we have looks like this. It's just a Curtis model, and I created this myself. I just added plausible values to it because I don't have access to any good manufacturer's models for modern discrete devices, because not many people are making discrete devices anymore. And foundry models I also don't have, and even if I did, they're mostly proprietary, so I couldn't show them here. So this is a Curtis FET. You can see that I've moved some of the parasitics outside. This is a drain resistance, the gate resistance, and the source resistance. And I moved them outside so that I can put voltage meters and current meters at these points, and I can measure those quantities without the voltage drop across the resistors confusing things. I've also, because of that, I had to put the inductors on the outside too. Those are the parasitic inductances of the three terminals. And finally, I put diode junctions on the outside too. These model the gate to channel diode junction. This is a very primitive model. It goes back to the early days of Microwave Office, and it does not include those diodes, so we have to put those in. If you don't put those in, you can get unrealistically high values of things like gate to source voltage, and you'll get results that are very likely better than you would in reality. So the first thing I want to do is run an IV curve for the model. So let's set it up here. This is the IV sweep. It's very easy to set up. You just drop your IV measuring device in and set up the sweep. It's 0 to 4 volts at the drain, and I've set it up for -1 volt, which is a pinch-off voltage, to plus 0.6 volts at the gate. And here is our FET IV sweep. Oops, get that right, FET IV sweep. Always helps to click on the right thing. And you can see I've run everything already here, but I'll click on the run button again just to be sure everything's up to date. And you can see the IV sweep, and that looks pretty reasonable too. It is pinching off at -1 volt and plus 0.6 volts, we're getting about 100 milliamps. So that all makes sense. Now, the other thing I want to do, get this out of the way, is run some S parameters. So let's do our FET S parameter test here. And you see I've taken the FET here. I've added bias T's at the input and the output, and bias sources of 2.5 volts. In this case, it's -0.5 volts, but I can adjust that to any value I want. Now, one other thing I should say very briefly here is that when you take that FET from the list of subcircuits and drop it into this test circuit, it's just going to look like a 2-port box, and you might not want that. You might want to see a FET symbol there. So you can easily go to the properties, right-click properties, and here under symbols, there's a listing of all the symbols in the program, anything you possibly want. That is the right number of terminals. Anyway, there's even more than this. And what I recommend you do if you want to change the symbol is go to the symbol file, system.syf, and that's right here. That contains all the basic model symbols in the circuit, all the resistor, capacitor, FET, bipolar, all of that stuff. You can see I've selected one here, which is the FET model at system.syf. Now, system.syf also includes things like resistors and capacitors and inductors and all those basic things. And you can probably find anything you want in here. Now, you won't see them right here because this is a 3-terminal device and it lists only the 3-terminal models. Obviously, you don't want to put a resistor symbol in here. So it doesn't list them. But that's one thing you can always do, and it makes your project a little more legible and easier to understand, especially if you show it to the boss. So anyway, that's one thing you can do. Now for the S parameters, let's take a look at the S parameters. I'll run this and update that. And now you can see this is S11 and this is S22, right? No, I got it backwards. Obviously, this is S22 and this is S11, I'm thinking. And they're doing about what you would expect to do. That is, they start out here high. S11 is essentially an open circuit at very low frequencies, and it becomes something with some input resistance and capacitance at higher frequencies. And S22 does something similar, although it's finite at lower frequencies. Everything here is what you would expect to see. So that's doesn't tell you anything about the accuracy of the model, but it does tell you that it's plausible. Now, if we take a look at S12 and S21, I put these on polar plots. And you can see here S21 starts out with a magnitude of about 4, and it gets smaller and the phase changes in the way that you would expect it to. Very much the same with S12, except it starts out smaller in the center of the plot, and then as you move to higher frequencies, it becomes larger. And the initial phase is about 90 degrees, which it should be. So all of that looks good. All of that makes sense. You notice that the plot, the cursor here, when I drag it over the plot, is in magnitude and angle. By default, that plot is in real and imaginary. And if you're like me, you probably want to see magnitude and angle. Most of us, I think that way. But you can change that very easily. Just go to the plot setup, and the easiest way to do that is double-click on the legend and go to markers, and then where it says display format, go from real imaginary to magnitude and angle, as I have already done here, and then you'll get real and imaginary, rather magnitude and angle, just as you wish. Okay, so you look at all these things, this all makes sense, it all looks plausible, and I'm going to trust the model then. Now let's take a look at the FET circuit itself. I always like to start with an ideal circuit and then get that working and then replace the ideal elements with real elements. That's a lot easier and more satisfying, I think, than trying to put it all together, run the simulation, discover that it doesn't work very well, and then try to figure out what to do to make it work well. If you start out with an ideal circuit, it's very easy to get it going, and then you can replace an element with an ideal element with a real element and readjust things so it works, and just keep doing that until you have a completed circuit. That's the way I do things. It's not the way everybody does it, but it works for me. So you see what I've got here. I've got our FET, and I have at the input bias voltage. It's a little below pinch off, as I said we wanted. And I have an inductor for tuning it at the input, and I have another stub here. This is a third harmonic stub. I found that it helps to have it there. It's 90 degrees at 15 gigahertz. At the 5 gigahertz input frequency, it just adds a little bit of capacitance, which you can easily tune around. This line is mainly for bias. It's 90 degrees at 5 gigahertz, 70 ohms, but it also will short circuit the gate at 10 gigahertz, because this is a quarter wavelength shorted here. Since it's half wavelength at 10 gigahertz, it'll be shorted here too. And we do something similar at the output. Here we have a 10 gigahertz line, which is 55 degrees now. Originally it was 90 degrees. And so 90 degrees at 10 gigahertz, that's just fine for injecting the bias. And here we have a quarter wavelength stub at 5 gigahertz, open circuited, which short circuits the drain at 5 gigahertz. This is extremely important. Now, I strongly recommend that once you have this stub adjusted to the right length and frequency, leave it alone. There's going to be an overwhelming urge to use this to tune the output of the multiplier. And it's going to be very effective, of course, because you change it a little bit, it'll have a big effect on the multiplier's tuning. But it will also leave you in a situation where the fundamental frequency output of the multiplier is not minimized anymore. You get a lot of fundamental frequency leakage, and you really don't want that to happen. This stub is for that purpose only. Adjust it for that purpose, and don't mess with it anymore, unless of course you need it to, because some additional capacitance or other parasitics pulls it off frequency a little bit and you need to readjust it to short circuit the fundamental. But that's the only thing that it should be for. Don't use it as a tuning adjustment. Now, as I said earlier, you can see that this line is 55 degrees, not 90 degrees anymore. And I use this as a tuning adjustment. It creates a little shunt inductance in the output, which is just what you need to tune out the parasitic capacitances. So that's legitimate to do, no problem there. Of course, you then need to be sure that you've got a good short circuit here, but that's the difference between the ideal circuit and the real one that I'll show you next. Now, one thing I may have said before or not, I'm not sure, is that it's very helpful to set up the project hierarchically, and you'll see a lot more of why that's helpful as I go on. But here's a test setup that I have. The ideal multiplier is here, and I have a swept frequency source, which is also swept in power, and I have a load. So I will set up the, here we go, multiplier output power versus frequency. And we'll sweep that. Okay, there it is for the ideal circuit. Now, I've already done the adjusting and tweaking and so on, so this is about where I want it. You can see that the fundamental frequency output is like nothing. And that's simply because I'm using an ideal stub. Ideal stub is a perfect short. You're not going to get this in reality, but at least this tells you that that stub, that 5 gigahertz quarter wavelength stub in the output is doing what we want it to do. And things are tuned up a little bit here very nicely so that I'm getting Well, according to this, about 13 dBm, and it's centered on 5 gigahertz. And that's what you want to accomplish with the ideal circuit. And then once you have it basically working like that, you can start replacing those ideal elements with real ones and get a more practical circuit. The other thing that's worth looking at before we go away is to look at the input impedance. And I'm looking at the input impedance here. You can see that I've adjusted the imaginary part, so it's pretty close to 0, it's about an ohm. And the real part I don't care very much about. It's up around, it looks like a couple of ohms, I guess, at maximum output. So that's pretty good too. And this was done mostly just by adjusting that input inductance. Oops, wrong thing here. Here we go. Mostly by adjusting this input inductance. And that was that. Now again, before I get too far along, I will show you some things that I should have shown you a little while ago. That's setting up the project options for this. Now the project options, the number of harmonics and things like that apply to this top level subcircuit. It doesn't apply to the frequency multiplier subcircuit here. You notice these are 50 ohms. Those just indicate ports that impedance is not used once you use it in a subcircuit. So in the, use it as a subcircuit in a top level circuit. Now in the top level circuit, the load impedance is 70 ohms, and that's what matters. Now over here, I have taken my ideal multiplier circuit and converted it to a more realistic one. You can see what I've done. I've added some things here like vias for the source connections, a little line here, some lines here for interconnects for the drain and the gate. My stub is still here, but there's a T now. And the parasitics of that, rather it's a cross, I guess, the parasitics of that cross are going to affect this stub, that is the frequency at which it shorts everything out. So I had to adjust the length a little bit to optimize that. And this is a transformer to get me to 70 ohms from the roughly 50 ohms that I had before. And, you know, some little things like that. So what else can I show you? Over here, there's some tuning. My inductor has been replaced by a high impedance line. These stubs are still pretty much the same. And the capacitors are now chip capacitor models. I think at 5 gigahertz, they should be fine. At 10 gigahertz as a blocking capacitor, they're fine too. But for bias stub, I've used a distributed element. Now, here's one reason why I always suggest that people do these things hierarchically. This is my test circuit here. I was using it with the ideal multiplier, but now I can change this from the ideal multiplier to the regular multiplier, this one over here. And now I don't have to change the plots. I don't have to change really much of anything except that one selection you just saw me make. You may note also that I don't have to change the setup for this project because the setup for this multiplier, this real multiplier subcircuit is going to be the same as for the ideal one, and there's no reason why they should be different. Actually, there's one thing I do have to change, although it probably won't make a huge difference. You notice this load impedance is still 70 ohms left over from the ideal circuit. We'll make this 50, and I can do that because I have added a little transformer section in here so that it transforms the 50 ohm load to the 70 ohm load that I decided was optimum. So here we are, there's our circuit. We can run the simulation and take a look at the multiplier's output power. This is at the center frequency and input versus output power. And here's the multiplier's power versus frequency, which shows that we do indeed have minimum fundamental frequency output. That's the red plots here, minimum fundamental frequency output at 5 gigahertz, the way it's designed. And that fundamental frequency is set up on this scale over here on the right. The left scale is the output power. So you can see it's peaking around 12 dBm output for 12.7 output for 12 inputs. So it's about unity gain. And that's pretty much it. That's all you have to do. And you have a frequency multiplier.